Hello, grade 11 chemistry students. This is a video talk through of PQ10, which is the Gay-Lussac law, the pressure and temperature law, and then the combined gas law. The combined gas law is going to put together all of the other three gas laws that we have learned individually. So that's Boyle's law, Charles' law, and Gay-Lussac's law can all be put together into what is called the combined gas law. Because in reality, it can be very difficult to hold constant one of those three variables, either pressure, temperature, or volume, to use only Boyle or Charles or Gay-Lussac. So that's the reason for the combined gas law, is when we have multiple variables changing. So here we go. This is number one. Number one is a conceptual problem, a fill in the blanks problem. There is a word bank here for you. So Gay-Lussac's law is an ideal gas law. We're at constant volume. So in Gay-Lussac's law, volume is held constant. And the pressure of an ideal gas. So again, all of the gases we're dealing with in this chapter are considered ideal gases. They all behave in all of the gases that we're dealing with behave in an ideal way. What that boils down to is that it doesn't matter what gas we are speaking of, whether it's hydrogen or oxygen or air or anything. They all have similar properties, and that's true at what are normal temperatures and pressures. If you get into the fringes of temperature and pressure, very high or very low, different gases start to behave with different properties, but we don't go to those extremes. So all of our gases are ideal. So Gay-Lussac's law is an ideal gas law. We're at constant volume. The pressure of an ideal gas. Oh, that's a typo. That should be in Kelvin. Oh, sorry. What am I doing? I'm looking at the wrong thing here. Gay-Lussac's law is an ideal gas law where at constant volume, the pressure of an ideal gas is directly proportional to its temperature in degrees Kelvin. So we have to use the Kelvin scale here again. Basically, the importance of this gas law is that increasing the temperature of a gas causes its pressure to rise proportionally assuming the volume doesn't change. Similarly, decreasing the temperature causes the pressure to fall proportionally. So if pressure goes up, temperature goes up. If pressure goes down, temperature goes down. They move together in a proportional way. Okay, a few multiple choice questions, a few more conceptual ones before we get into some calculations. What temperature scale must all temperature units be converted to? Well, that is Kelvin. Okay, it all has to be Kelvin because we can't deal with negative numbers or zero as the temperature unit. That would make this temperature zero, and we're going to be dividing by zero, and that's just not allowed. Which variables must be held constant for Gay-Lussac's law to apply? Well, the volume and the amount of gas needs to be held constant. How many degrees Kelvin is absolute zero? Zero. Okay, moving into some calculations. So here we go. So determine the pressure change when a constant volume. So constant volume, we're going to know we're going to be using Gay-Lussac's law here. Determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 degrees to 30 degrees Celsius. So we need to convert these temperatures from Celsius to Kelvin. And I'm going to do these questions with a little list of the variables I have and what I need. So we have pressure 1, that's 1 atmosphere. T1, so it's heated from 20 degrees to 30 degrees. And the temperature here is going to be 20 degrees Celsius, which is 293 Kelvin. So remember that the Kelvin scale, the temperature in Kelvin, is equal to the temperature in Celsius plus 273. So 20 plus 273 gives us 293. Pressure 2 is what we're looking to find in this problem, and T2 is going to be 30 degrees Celsius, which is 303 Kelvin. Okay, so now we know that P1 over T1 is equal to P2 over T2. So let's plug in what we know and solve. So we have 1 atmosphere over 293 Kelvin, and that is going to give us P2, which we're looking to solve for, over 303 Kelvin. Whenever you get a proportion like this, you can go across the diagonal and divide. Cross, multiply, and divide. So that is going to give us 303 times 1 divided by 293, and P2 will come out as 1.03 atmospheres. And whatever pressure unit you start with is the same pressure unit that you finish with. Now, let's just inspect that that answer makes sense. So the temperature increased a little bit. It increased from 20 degrees to 30 degrees. So that must mean that our pressure also increases a little bit. And it did, from 1 atmosphere to 1.03 atmospheres. Okay, number 6. A gas has a pressure of 699 millimeters of mercury at 40 degrees Celsius. What is the temperature at standard pressure? Well, let's look at that first. So standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. So atmospheres is the easiest standard temperature and pressure to think of, but it would also be at 0 degrees Celsius. And if we convert our atmospheres to millimeters of mercury, that is 760 millimeters of mercury. 1 atmosphere is equal to 760 millimeters of mercury. So I'm going to work in millimeters of mercury in this problem. The temperature doesn't, the temperature does matter. It needs to be converted into Kelvin first. So let's make our little checklist of what we have. So we have P1. So that is okay. So the pressure 1 is 699 millimeters of mercury. T1 is 40 degrees Celsius, which is going to be 313 Kelvin. Again, I just add 40 to 273. P2 is going to be our standard temperature, so 760 millimeters of mercury, and T2 is what we want to find. Okay, so P1 over T1 equals P2 over T2, And let's plug our values in. So 699 millimeters of mercury divided by 313 Kelvin is equal to 760 millimeters of mercury divided by T2, cross multiply, divide by what is left, and you should get here a value of T2 that is 340.3 degrees Kelvin. Now, does that number make sense? The pressure increased from 699 to 760, so the temperature must also increase. Okay, number 7. If a gas is closed in a container, if a gas in a closed container is pressurized from 15 atmospheres to 16 atmospheres and its original temperature was 25 degrees Celsius, what would be the final temperature of the gas? That is going to need Gay-Lussac's law. So P1 is 15 atmospheres. P2 is 16 atmospheres. T1 is 25 degrees Celsius. So that is 298 Kelvin. T2 is what we want to find. So P1 over T1 equals P2 over T2. 15 atmospheres over 298 Kelvin is equal to 16 atmospheres over T2. Cross multiply and divide. So T2 is going to be 317.9 Kelvin, which again makes sense. The pressure increased from 15 to 16 atmospheres, so then the temperature must also increase. Number 8. A gas takes up a volume of 17 liters, has a pressure of 2.3 atmospheres, and has a temperature of 299 Kelvin. If I raise the temperature to 350 Kelvin and I lower the pressure to 1.5 atmospheres, what is the new volume of the gas? That is a lot of information given to you. We have information on volume, we have information on pressure, we have information on temperature. We know 5 things, in fact, and we're looking to solve for the 6th. So that is going to require the combined gas law. So we need for this, we need P1, we need V1, we need T1. We have P2, we have V2, and we have T2. Now, what do we know? A gas takes up a volume of 17 liters. It has a pressure given. It has a temperature given. So those are going to be our 1 values, P1, V1, T1, because it tells us the question, if I raise the temperature to some new value, 350 Kelvin, and lower the pressure, what is the new volume? So it's V2 that we're looking to solve for here. Okay, so P1, 2.3 atmospheres. V1, 17 liters. T1, 299 Kelvin. P2, 1.5 atmospheres. V2 is what we're looking to find, and T2 is 350 Kelvin. So what can we predict this new volume might be? Will it be greater than 17 or less than 17? And maybe how close will it be? Well, we can see that the pressure has decreased. So thinking about Boyle's law, when pressure decreases, the volume might go up because of Boyle's law. And in T1, the temperature increased from T1 to T2, so the volume should go up again according to Charles' law. So if we increase the temperature, we should increase the volume. So we should see a volume that is higher than 17 if we've done this correctly. So P1 V1 over T1 equals P2 V2 over T2. P1 is 2.3 atmospheres. V1 is 17 liters. T1 is 299 Kelvin. P2 is 1.5 atmospheres. V2 is what we want to find, and T2 is 350 Kelvin. Now, the goal here is to solve for V2 to get V2 all by itself. So we have to do a couple of steps of algebra in this problem. And let's go ahead and do that. I'm going to have to use up a little bit of space on the bottom. So we're going to multiply by 350 Kelvin first to get rid of that. And then we're going to multiply this side by 350 Kelvin. So that is going to give us 2.3 atmospheres times 17 liters times 350 Kelvin over 299 Kelvin. And that is going to equal 1.5 atmospheres times V2, which is what's left. Now we need to divide this side by 1.5 atmospheres to cancel out that. And then we need to divide this side by 1.5 atmospheres. That is going to leave us 2.3 atmospheres times 17 liters times 350 Kelvin divided by 1.5 atmospheres times 299 Kelvin. So now, if we look at our units, kelvins are going to cancel out on the numerator denominator. Atmospheres are going to cancel out in the numerator denominator, leaving us only a volume of liters, which is what we are looking for. You're going to do all of the math here, 2.3 times 17 times 350, divided by 1.5 times 299, and that will all work out to 30.5 liters. 30.5 has increased from 17, so our prediction holds true. All right, number 9. A gas has a volume of 28 liters and a temperature of 45 degrees Celsius and an unknown pressure. It has its volume increased to 34 liters and its temperature decreased to 35 degrees Celsius. If I measure the pressure after the change to be 2 atmospheres, what was the original pressure of the gas? So that's P1. That's what we don't know. Excuse me. V1 is given to us as 28 liters. T1 is 45 degrees Celsius, so I'm going to add that to 73, and I'm going to get 318 Kelvin. P2 is what we are told is 2 atmospheres. V2 is 34 liters, and T2 is 35 degrees Celsius, so that's 308 Kelvin. Making our prediction. Looking at Boyle's law for the relationship between pressure and volume, the volume has increased from V1 to V2. And what that should mean is that the pressure will have decreased. So P1 should be higher than P2. So given that the volume increased, the pressure should have decreased. So from Boyle's law, we can see that pressure 1 should go up, according to Boyle's law. Now, according to Gay-Lussac's law, between the pressure and the temperature decreased from T1 to T2. So that should mean that the the pressure should have also decreased from P1 to P2. So we should again see the pressure of P1 being higher than P2 according to our numbers. So let's see what happens here. So P1 times V1 over T1 equals P2 times V2 over T2. I'm going to rearrange this equation before I plug in numbers, just as a different method. You can do the algebra however you see fit, but I'm trying to solve for P1. So I got to move T1 over, and then I got to divide by V1 in order to get that. So that'll leave us is P1 is going to be equal to P2 V2 times T1, because I multiplied by T1, and T2 times V1, because I divide by V1. Okay, plugging in what we know. P2 is 2 atmospheres. V2 is 34 liters. T1 is 318 Kelvin. T2 is 308 Kelvin, and V1 is 28 liters. Okay, plug and chug into the calculator here. P1 should work out to 2.51 atmospheres, and as our prediction said, the pressure increased, started at a higher value for P1 and then decreased as we moved to P2. So it started at 2.51 and ended at 2.0. All right, and our last one before we do a couple of conceptual problems is number 10. So number 10, I have an unknown volume of gas held at a temperature of 115 Kelvin in a container with a pressure of 60 atmospheres. If by increasing the temperature to 225 Kelvin and decreasing the pressure to 30 atmospheres, that causes the volume of the gas to be 29 liters. How many liters of gas did I start with? So P1 we know to be 60 atmospheres. V1 is what we want to find. How many liters did I start with? T1 was 115 Kelvin. P2 is 30 atmospheres. V2 is 29 liters. And T2 is 225 Kelvin. So looking at our relationships here again, the pressure decreased from 60 to 30. So that made the volume 29. So the original volume should have been lower, right? We decreased the pressure. So then we should increase, the volume should be increased. Okay, so we are, sorry, 1 second here, you guys. All right, you guys, sorry about that. Just needed to move away from my computer for a second. So let's look at a prediction here of what this volume will be. So according to Boyle's law, so let's actually write this out explicitly. So according to Boyle's law, if the pressure decreased from P1 to P2, that must mean that the volume would have increased from V1 to V2. So V1 must be less than V2. The volume will have to increase if the pressure has decreased. So now let's look at the relationship between volume and temperature. So that would be Charles' law. If the temperature increased from T1 to T2, the volume must have also increased from V1 to V2. So again, we would know that the volume 1 must be less than the volume 2. So our number should come out to less than 29. Okay, so let's solve here. P1 V1 over T1 equals P2 V2 over T2. Again, rearranging, I'm going to rearrange this first. So I'm going to multiply this side by T1, and I'm going to divide by V1. And I got to do the same thing on this side. So I got to multiply by T1, and then divide by V1. So that's going to make, not divide by V1, divide by P1. P1 doesn't change anything too much though. So that leaves us for V1, P2 times V2 times T1 over T2 times V1. And now let's plug in our values. P2 is 30 atmospheres, V2 is 29 liters, T1 is 115 Kelvin, T2 is 225 Kelvin, and P1. Oh, I made a little mistake here. I realized I went with my V again. This should be P1. P1 is 60 atmospheres. So we can see that our atmosphere unit cancels out, our Kelvin units cancel out, leaving us only with liters. Plug and chug, 7.41 liters. And that makes sense. We predicted that volume 1 should be less than volume 2, and we did that with Boyle and Charles' law, and it is. All right, couple of conceptual problems to finish off this set of practice questions. Explain why a car tire swells in hot weather and somewhat flattens in cold weather. Okay, so what's happening here is as the temperature rises, the air molecules in the tire move faster, right? They have more energy. So they collide more frequently. They're moving faster, so they collide more frequently with the inside of the tire. This increases the pressure and pushes out the tire more. Swells. The opposite happens in cold weather. So if you were watching this video in the wintertime, which it is right now when I'm filming it, you want to make sure that your tires are inflated properly. It's hard on your vehicle, the shocks on the struts in your vehicle if the tires are low pressure, and you also get worse gas mileage if you are driving with underinflated tires. Okay, number 12, explain why the lid on a tennis ball canister will pop off easier in warm temperatures. It's really the same idea as number 11. So I'll just phrase it in a different way. Increased temperature means increased pressure on the lid of the can, causing it to pop off. There you go. Thank you very much.